the 1W-MINDS. Okay, welcome everyone. Today we have Pablo Groisman from the University of Buenos Aires, where he did his PhD and now he's a full professor. And he's going to talk about learning distances to learn topologies, to learn dynamical systems, to learn chaos.
Okay, thank you, Sole. Thank you guys for the invitation. It's a pleasure to be here with you. So that's the title. So although the title looks like a lengthy and maybe complicated, what I'm going to talk is something which is very simple. At least I think it's very simple. So please feel free to stop me at any time and ask any questions, because I think we can like flag together till the end of the talk. So the motivation for what I'm going to talk about, well, first here is the list of collaborators. These are we are working on this topic from some time ago with all these people. Eugenio Borghini and Jimena Fernandez, they are topologists. They know much more topology than what I know. Nicolas Chevar, he's now in the industry, but he graduated from our university last year. Mathieu Jonker, he's in Toulouse, he's a probabilist as me, and Gabriel Milding, he's a physicist. He works with the dynamical systems. He's the guy from dynamical systems. He works with studying how the birds learn to sing. And Facundo Sapienza is now in Berkeley. Esteban Tabac, who's from Courant Institute, New York University. So the motivation, well, I will tell you in a minute what's the motivation. First, I will state the problem, which is very easy to state. So suppose that we have a d-dimensional manifold, we call it M, in some high-dimensional space. It could be a high-dimensional space or not. We use capital D for the dimension of the ambient space, and the manifold has dimension small d. So it could be, as in many situations, that small d is much smaller than capital D, but there are also some other situations in which it's not the case, and this is also useful. So we assume that we have endpoints in this manifold. You can think of endpoints draw IID independently from some common distribution with density F, which is a density on the manifold. So these random variables are not continuous in the whole space, but they are continuous in the manifold. And we want to understand, so this is what usually is called the manifold hypothesis, is that you have data in a high dimensional space, but you assume that your data lies in a manifold of much smaller dimension. So what we have is like m points in this manifold, but we don't know what is the manifold, we don't know what is F, and we want to understand what is the geometry of this manifold, what is this density, what is the topology. For example, we will see that in some applications, it is important to understand what is the topology of this manifold. And the picture we have in mind is something like what you see here, is that we have some kind of manifold, and there is you can think like you have a bimodal density there. So here this violet and green things represent the sub-level curves of the density. So you can think here as like we have like a Gaussian here and some Gaussian with much smaller variance here. And we would like to understand first what are the distance between 2 points. For example, here in this manifold, let's say we want to understand what is the distance here. And of course, you can think on geodesic distance, for example. And this is related to a very well-known tool, which is called ISOMAP, which estimates geodesics in this setting. But we want something else. We want not just like to estimate geodesics. Well, in fact, ISOMAP is much more than estimating the geodesic, but they use it's an intermediate step to get a multidimensional dimension reduction of the data set. So we would like to hear another notion of distance, which takes into account the geometry. So it will be some kind of geodesic, but we would like also to take into account what is the cloud of points, let's say the density, for example, of points, in the sense that, for example, if we get this situation, we have here x1, which is the center of one of the Gaussians, and x2, which is the center of the other one. And we have some point here that we call x tilde. Somehow we would like, suppose that we want to do some clustering, we would like to group x tilde with x2 rather than with x1. And so we would like some kind of distance such that x tilde is closer to x2 than to x1. So that's what we are looking for. And so, as I said, this is important in applications if you want to estimate dimension, distances, and the topology, is going to be important to understand the whole geometry and topology of the manifold. So what are the motivations? So one possible application is to do dimensionality reduction. So it's once we know what is the manifold, we can represent our data with much smaller variables than what we have, like the dimension of the ambient space. We can use this to do, once we have the dimensionality reduction, we can use it to do clustering, as we will see. And there is another motivation that we have in mind, and that's in fact, this is the reason why we start working with part of this project, is to fit a chaotic dynamical system that we are going to discuss in a minute. What does it mean to fit a chaotic dynamical system? So it sounds like something which doesn't make sense at all. So here is one example. I guess I can assume that everybody is familiar with the Kmeans algorithm, right? So maybe you tell me if should I explain what is Kmeans, or can I assume that? Okay, I will assume it. You tell me if it's not the case. So suppose that we do Kmeans. Kmeans is just like an algorithm to group your data in K groups. And it is well known that Kmeans essentially is going to separate your data with hyperplanes. So if you have this data set, which is these three circles, and you do Kmeans, what you're going to obtain is those three groups, the red, the green, and the blue, which is not what you expect. This is a very well-known failure of Kmeans. But what I'm going to show by the end of the talk, that if we do Kmeans, so Kmeans is an algorithm that is strongly based on a notion of distance. What you do is that you look for if you are looking for three groups, you look for three centers, and then you assign each of your data points to one of those centers in such a way that you minimize the overall distances. You look at the distance from each data point to one of the centers, and you want to minimize the sum of all the distances. So the notion of distance is very important. If you can think of the distance as an input, and usually what is used is the Euclidean distance. And when you do Euclidean distance, that's why you fail finding these groups here, because you try to separate with hyperplanes. But what we are going to see that if we replace this distance with another notion of distance, an adequate notion of distance, we can use the very same K-means algorithm to obtain a nice separation in groups. So that's somehow some kind of a take-home message. We can still use K-means if we use it with an adequate distance. So having a good notion of distance could be very important in several applications. Okay, so the other promise is that we can use this notion, this distance that we are going to develop to validate a model for a chaotic dynamical system from data. So the problem is that, well, let me tell you what's the situation. So suppose that you have this data set. It's a time series. And in fact, this time series comes from measuring the air sac pressure during the birdsong in a canary. Okay, so you get this time series, and let's say you want to understand this time series. For example, you want to know if you can think of if this series comes from projecting in one variable a dynamical system. So is it true that there is a dynamical system? Let's say it's not going to be a one-dimensional dynamical system, but maybe it's a three-dimensional, four-dimensional dynamical system. And this is the projection of one of those variables. So that's a question that a lot of researchers deal with. So there's a way to answer this question. So the first thing is that there is something which is called Kmeans embedding. There is a way to embed this time series in a maybe three-dimensional, four-dimensional space. I'm going to explain maybe later on what is the way in which this embedding works, but let's just for now, believe me that you can embed this. So assuming that this time series comes from a dynamical system, you can embed this projection. What you get is just the projection of one of the variables over a one-dimensional space. So from this data, you can embed this data in, let's say, in a three-dimensional space, and you get a curve. And if it is the case that this data comes from a dynamical system, you are going to recover this dynamical system. You are going to get something which is equivalent to the original dynamical system. So it's some kind of magic, but it's true. So you start with a dynamical system, you project over one variable, you get a one-dimensional measuring, and then you can, from this one-dimensional measurement, you can recover your whole dynamical system back. So that's Kmeans. So once you have that, so we would like to understand, okay, so what's the dynamical system? What are the equations? Or let's say it easier. So suppose that I have a model, I have a proposal, I have a set of equations that I think they can fit the model, and I want to check if my model is okay or not, if it fits the data or not. So the problem if there is such a dynamical system, you expect the dynamical system to be chaotic, because otherwise you cannot have this kind of behavior. So if you have like a system which is not chaotic, what you're going to say is that you start at some place and you're going to get always the same thing. You're not going to change your regime. The only way in which you can stay like for some time, let's say you have this, for some time you have this behavior and then you change to this behavior. Well, the only way you can have that is that you are sensitive to initial conditions. You are behaving with some kind of you are having some kind of behavior, and suddenly you change to some other regime. So when you have a chaotic dynamical system, you cannot just like, let's say if my model fits the data, because it is chaotic. So the model doesn't fit itself. So you need other tools. And the way in which you try to understand this is if your model, if your proposed model is qualitatively equivalent to what you see. So you want to understand if the data qualitatively is equivalent to your model. And this means, for example, that when you look at the manifold and the attractor, for example, if you have an attractor in your dynamical system, you want to see if you can reproduce the geometry and the topology of that attractor. So in this case, for example, you do this Kmeans embedding, and what you get is this mess here. And observe that when you have something like, for example, this part of the data, which is you can think of this as a periodic thing. When you have something which is periodic and you embed this, what you expect is to have a cycle, because it's something which is repeating itself again and again. So you will expect here to have like here one cycle, here you expect a different cycle, then another cycle, and then another cycle. So you expect to have 4 cycles, and that means that there's no manifold in this case, but what the attractor that you're representing. Here, you expect to have something with 4 cycles, 4 different cycles. And in fact, you can see them here, that you have exactly 4 different cycles. So the idea is to develop a tool to receiving some time series and say, okay, this is what you have here is 4 cycles or 3 cycles or whatever. So by the end, we are going to apply a method which is called persistent homology, that I'm not going to talk about it now. We are going to talk about that later. But essentially, is that from this data, you can do this thing which is called persistent diagram, and you can read this. You have the blue points and the orange points. Blue point stands for H0, which is the homology group of order 0, which is the number of connected components. And you should read this point here as having 1 connected component. And orange stands for a homology group of order 1, which means number of 1-dimensional holes, which are represented by cycles in this case. And the way in which you should read this is that here there is 1 hole, 2 holes, 3 holes, 4 holes, and all this part here is essentially noise due to the fact that we are dealing with a finite sample and not the whole space. In the limit, you expect not to have all this part here. Okay, so that's the end of the story. This is some kind of a spoiler. So let's back to the basics. So if somehow you are lost here, so this is a good time to start from scratch again. So I'm going to start with my original problem. We have endpoints, and we want to understand the geometry of that cloud of points. So there's a topic which is it's very important in the probability community, which is called first passage percolation. And among those models studied by first passage percolation, there is one which is called Euclidean first passage percolation, that was introduced by Douglas Howard and Chuck Newman some time ago. And so you start, the model is as follows. So you start with a random set of points. You can think of a Poisson process or any finite set of points. So they consider a Poisson process, but as you will see, you can define these things for any finite set of points. I guess there's something. Okay. For that. Okay. I don't know what it thanks says, sorry. I thought there was something in the chat, but not the case. So so this is what the distance that Howard and Newman introduced. So you fix 2 points. Suppose that you consider this point and this point, and we are going to consider the following distance. We consider all possible paths. You can think of the complete graph of these points. And you consider all possible paths from here to here. All possible paths means that you go from this point to some other point, and then from some other point, some other point, and some other point. And the cost of each path is going to be the sum of their lengths. Okay, so this is the path. And you consider the sum of the lengths, but this is Euclidean distance. And then you raise them, each length, you raise it to a power alpha, okay? So it's easy to see that if alpha is 1, so you do nothing, there's no power there. Well, then you consider the path with smallest cost, okay? So you get some kind of optimal path respect to this cost. So when, as I said, when alpha is 1, the optimal path is just go directly from your point, let's call this x and y. The optimal path for alpha equals to 1 is just go straight from x to y. So this is for alpha equals 1. But if, let's say that alpha is 2, if alpha is 2, what you pay is the diameter. So you can consider, for example, the ball here. And what you pay is the, let's say that you're in dimension 2, you pay the diameter raised to the square. So this is proportional to the area of this circle. Okay, and in general, if you raise your distances to the dimension of the space, what you get is the volume of a ball. So the cost here of each path is going to be proportional to the sum of all these areas. And then you can see that it's much cheaper to do small jumps than if you consider, for example, now the path that goes directly from X to Y. What you get is some kind of this thing, which is well, it has a cost which is much, much larger. Okay, so the message here is that when alpha is larger than 1, large jumps are discouraged. And the larger the alpha, the more are discouraged these jumps. Okay, so this was introduced in the setting of Euclidean first passage percolation, and the motivation there is completely different from what we have here, but it's very useful. So, and as you see, this can be defined for any finite set of points. And then we can use this distance. And that's exactly what we are going to do. So, because if now we have a finite sample, a finite number of points in a manifold, we can do exactly the same definition, and we are going to try to find the path from x1 to x2 that minimize this sum of the lengths raised to the power alpha, which means that we are going to move through regions where there are a lot of points, where the density of points is large, because in that region we are going to do small jumps. And in particular, it's going to prevent us to go away from the manifold. We're going to try to stay close to the manifold all the time, because moving far from the manifold, you pay a lot. Okay, so this is an example. Here it's in dimension 2. In fact, your manifold here is it's a square. It's a very simple manifold, but you have like the density which is not constant. So in this picture, you have two. Let's say that here the density is 2, and here the density is 1. So you have the double. Like you don't see all the points because there's an enormous number of points, and what you see just like they are not represented there, but you have a lot of points in this rectangle, and the density of points is twice in the dark region than in the light gray region. And here what you get is the optimal path that is obtained for different values of alpha. The green one is alpha equals 1.5, the blue one is alpha equals 3, and the red one is alpha equals 6. So what you see that the larger the alpha, you try to stay more time in omega 1, which means that because it's the region where you do small jumps. Okay, so the larger the alpha, the more you want to be, you do most of your path in that region. And you don't care about the length, the total length of the path. And what you see in black is what you get in the limit, that will be what we are going to talk about. What is the limit of these paths? Okay, so when you see this picture, maybe you already think of what is sometimes called the Lifeguard problems, or which also has some flavor to Snell's law. So this is the Lifeguard problem. If you want to rescue someone which is in the sea, you don't walk straight. You do most of the part of your walk or your run in the beach, and then you swim for a shorter time in order to minimize your total time to reach the guy. And this is exactly the same thing that the light, that the array of light tries to do. And that's Snell's law when you have like this situation where you have just two densities, two constant densities, but in general it's known as a Fermat principle in optics, that the light tries to minimize, or in fact it tries to, the path that light uses to go from one point to the other, it's an extreme of the function that gives you the time it takes. Okay, so it tries to minimize or to find a critical point for that function. So inspired in that principle, we decide to call this distance the Fermat distance that comes from there. But I should say that there's also an independent group that introduced this distance, and they call it power weighted. I forget one, no, power weighted. I missed something here, distance. And this is Tamerlane, Mackenzie. Okay, so that's the distance we're going to work with. And we want to understand what is the limit of this distance. So as a guess, if you want to guess, what we see is that, okay, we want something that tries to go through regions in which the density is large. We like regions with large densities. We don't like regions with small, where the density is small. So we are going to define what is the limiting object, which we should call it population Fermat distance. Okay, as always in statistics, we have a sample, and we have a sample statistics, and then we have the population, and we want to prove conversion from the sample, let's say sample mean to the population mean, sample variance to population variance. Here we are going to try to prove the convergence of the sample Fermat distance to the population Fermat distance. So we want to understand what should be the limiting object. And so we take our density in M. This is a picture we already have in mind. And we are going to consider the following distance, which is a geodesic distance in the manifold respect to some Riemannian metric in the manifold, which is not the one given by the natural inner product. So we consider the following thing. So for any pair of points in M, we fix a parameter beta, and we are going to consider the integral, the path integral for a path that goes from X to Y. We are going to consider the path integral over gamma of 1 over f to the beta. Okay, that's the cost of each path. And then we are going to look for the path that minimize this quantity over all paths. If you want to consider path on the manifold, you can consider path on the manifold. If you want to consider any path, it's okay, because paths that are not contained on the manifold, you pay a lot because your density is 0. So you are going to pay infinity so that path, you are not going to choose one of those paths to minimize this function. And as you can see, this distance always is trying to choose, let's say, the geodesics respect to this distance. They're trying to choose regions where the densities are large. So if you do that, for example, in this case, in this situation, you expect x tilde respect to this distance to be closer to x2 than to x1, because you can go from x tilde to x2 through a region in which your density is positive and even maybe also large. But when you want to go from x tilde to x1, you need to cross this region here in which your density is very small or 0, and then you pay infinity, let's say, or you pay a large amount to go through that region. So this is in consonance with our empirical thing. And what we are going, well, first, this is, as we discussed before, this is a good distance, a good metric to do clustering, because we are going to assign x tilde to x2 rather than to x1. So here we have some heuristics of why do we have this conversion, but I think I'm going to skip this for now, and then in any case, we come back later. So I will skip to the theorem. So we want a theorem. So what kind of theorem are we looking for? We are looking for a theorem that somehow proves that what we compute with the data converges to something that depends on the distribution of your data. So one possible option is that, okay, we fixed 2 points, x, y. We compute, we have the data. We compute the Fermat, the empirical Fermat distance, we call it dxn xy. Maybe we need some kind of normalization, we'll see. In fact, we need some kind of normalization, we are calling it n to the beta. And we will like this, we can try to say, okay, this converges to what we call the population Fermat distance for each pair of points. That's good, and we get some theory, we get a theorem with that flavor, but that's not enough if we want to understand global properties like the topology of the manifold. Okay, so if we want to understand the topology, or we would like to say, okay, it's not just that for any 2 points the distances are converging. We would like to say somehow that the topology that we estimate with our points is converging to the topology of the manifold. And if we want that, we need something which is global for the whole manifold. So we are going to prove convergence not just for any pair of points, but convergence as metric spaces. So when we introduce this distance to our sample points, this gives us a metric space for the finite set of points. Okay, so we have a finite set of points, and of course, what we get the manifold with equipped with the population Fermat distance is also a metric space. So somehow we would like to prove convergence as metric spaces. So we need a notion of distance between metric spaces. So this is, fortunately, there is a notion of distance between metric spaces, which is called Gromov-Hausdorff distance. And okay, there is the definition, but it's not that important. The important thing is that you have like 2 metric spaces, and you can compute the distance between these 2 metric spaces. So we can do the following thing. We have our manifold. We have our finite sample containing the manifold, which is IID drawn from some density F. We have this parameter alpha, which gives the power at which we raise our length. And we are going to define beta as alpha minus 1 divided by d. That's just the computation that I'm not doing here. So we have the population metric space, as we said before, and we have the sample metric space, which is given by the sample with this distance. And the theorem that we proved, there are 2 parts. So the first part we did it with Mathieu Jonker and Facundo Sapienza, and the second one, which is this second part with the whole global structure, is with Eugenio Borghini, Jimena Fernandez, and Gabriel Midlin. And so far it's a preprint, it's not published yet. It says that when you compute the distance as metric spaces between these 2 things, this distance converges to 0 in probability, or in fact also almost surely. Okay, so we have convergence from these 2 metric spaces as n goes to infinity when you have an IID sample. Are we good so far? Any question or comment?
I think we're good.
Good. Okay, let's continue. So how can we do? So what can we do once we have defined this distance and we have these metric spaces that we know that our metric spaces computed with the sample converges to the metric space defined by the manifold with the density? We can use this for clustering. we can use this to do density estimation that leads to classification, for example, based on this notion of distance. We can do non-parametric regression. We can do optimal transport on manifolds. We've been working on one of these, and we're still working on others. And also we can do homology inference. And that's what I'm going to. So this homology inference means topology, means estimating the topology. And we're going to talk mostly about this last one. Okay, so what is homology inference? So it's a tool also used in differential geometry and in topology to understand the topology of a manifold. So suppose that you have a d-dimensional Riemannian manifold, which is embedded in RD, like this one, and you would like to understand from a sample. Okay, so that's the question: how to learn the topology of M from the sample. So here is the sample. So now the slide is complete. I'm going to start from scratch here. So we have the manifold, and we have a finite sample of the manifold, like here. And we want to understand what is the topology of this manifold. In this case, we would like to say, okay, there is one connected component. Well, as you see, there is one connected component, and there is a one-dimensional whole. There is one-dimensional whole, and that's it. We would like to answer that. Okay, so we would like to say that, but from the points. And so there's a way to do that, which is called persistent homology. It's a tool to do that. That essentially, I'm going to be very vague. What you do, you can think of as what I think what is something which is intuition goes with it. That is, okay, you can do, of course, if you want to say, okay, what's the topology of this finite sample of point? What you get is the discrete topology. So if you do nothing, you get something which is very bad. So what you get in a finite sample, what you get is n connected components, no holes, nothing. So that's very, very bad. But that comes, of course, from the discrete nature of your data, and you don't want that. So you can say, okay, I'm going to do small balls of size epsilon. And then we consider the union of these balls. And we would like to say, okay, my estimation of the topology of the manifold is the topology of the union of these balls. In fact, this is not what you do, because then you need an algorithm to compute this topology, and that's not as simple. You do something which is called, for those who are familiar with that, we do something different. It's something which is called the Rips complex. So what you do, if you want to compute the topology efficiently, like computing really, you need to you can compute topology or the homology for simplicial complexes. So you prefer, instead of having the union of balls, you prefer to have a simplicial complex, and for that you can compute, and just with linear algebra you can compute the homology. So the way to understand this thing, you can say, okay, I'm going to consider balls of size epsilon, and if I have a ball in which I have if there are 3 points in a ball of size epsilon, I'm going to put a triangle between these 3 points. If I have 2 points in a ball, I'm going to put an edge between these 2 points. And if I have 4 points in a ball of size epsilon, I'm going to put a tetrahedra for these 4 points. And that's the way in which you can construct a complex, and then you can compute just using, I'm not going to go into details, but just believe me that just using linear algebra, once you construct this complex, you can compute the homology group for this complex. So that's okay. So we have the finite sample, we compute, but here is what I said before, we do these balls, but the problem is that what I define depends strongly on the radius of these balls. If we consider epsilon very, very small, we are going to get a discrete topology, because we get essentially the same as the finite set of points. So when epsilon is very, very small, you get n connected components. That's what you see here, n connected components. And as far as you start rising epsilon, at some point you are going to get probably the correct topology. Here you see exactly the size of the balls at which is the last size of the balls at which you get the correct topology, which is the topology of the circle, just one hole. And you can see if you enlarge a little bit more these balls, then you're going to fail because you're going to answer that you have 2 holes, when the answer should be like you have just 1 hole. Okay, so what's the idea of persistence homology is that, okay, so you, instead of computing with 1 epsilon, you compute for all epsilons. And what you do a diagram in which you encode the information of the homology for all the values of epsilon. So what you do is, here you have birth, and here you have lifetime. So what you do is, so for example, for the connected components, you say, okay, when each connected component, I'm going to identify when, at which value of epsilon starts. We think this as a birth, and then at some time it dies out. And that's what we call the lifetime, from which epsilon, at which epsilon we start, and for how long we can see that feature, that topological feature. So in that way, here we have this all these connected components that started at time 0, and all these connected components finished or died before time 1/2. And there is one connected component here that started at time 0 and lives infinitely many time. Okay, so that's the real connected component. And what you see here is the same thing, but when we take into account the first homology group, which means cycles. Okay, so these 2 things means that you can see 2 cycles here. One that started at, let's say, this time here, 0.4, and lives for all this time, 1.4, and there is another one that started here and lives all this time. As you can see, they are like corresponding to this cycle and this cycle, and as you can see, this is not the correct question, right? So this is not okay. Okay, we will see that we can fix this. So this is a very well-known tool, which is called persistent homology. And as I define this diagram depends, or there is an input, there is a parameter, which is the distance you use to measure all these balls. And this diagram was done using Euclidean distance. That's the distance which is usually used when you construct these persistent diagrams. Okay, so let's see. So what are, of course, you can imagine what I'm going to say now. We are going to replace the Euclidean distance with this Fermat distance. So the idea is, instead of considering balls with respect to Euclidean distance, we are going to consider balls with respect to the Fermat distance. That is a distance that it's on the manifold instead of being on the space. And we can see that when we do that, we can get persistent diagrams that in which, like, topological features that you want to stay, they persist for much larger times. Okay, so this is the persistence diagram when you do the Euclidean distance, and when you do with one version of the Fermat distance, what you get is that, again, you have this connected component that started at 0 and goes up to 6, and you see one hole that started here, and that's it. And there is no second hole. You don't see it. And of course, what you see here is what I said before, is noise that has to do with the fact that when epsilon is very, very small, what you see is something which has nothing to do with your manifold. You see just the topology of a discrete set, of a discrete data set. Okay, so that's one good news. When we replace Euclidean distance by this Fermat distance, we get persistent diagrams in which topological features persist longer.
Can I ask a question?
Sure.
Is there a choice of beta that gives you the two components in this Fermat distance?
Well, if you consider it's, I guess you refer to the power at which you raise the distances,
Yes.
right?
Mm-hmm.
We call it alpha. So if you take alpha equals to 1, what you get is Euclidean distance. So for alpha equals to 1, what you get is exactly the same as before. Unless, so in fact, for different values of alpha, you get everything. So in fact, here what you see here is you see something which says KNN, so it's not exactly Fermat distance. So when you do alpha equals to 1, that's Euclidean distance. But if you do alpha equals to 1 and you consider your optimal path, but you restrict your search to path in which each jump corresponds to a nearest neighbor, like let's say like one of the fifth nearest neighbors, what you get is the distance that is computed by isomap. So that's the isomap distance, let's call it that way. So for different values of alpha, you can go over all these estimators as well. And of course, if you take alpha larger than 1, but converging to 1, at some point is going to appear this thing like this, the second hole, right? So you are going to see that when alpha is very close to 1. Did I answer your question?
Yes, thanks.
Good. Okay. So another good news is that we can also compute, or we can also prove convergence among persistent diagrams. So that's the way in which also you have the question, what is the topology of, or what is the homology of our manifold? And there is a nice answer to this question. You don't say, okay, you don't describe it with words, you can describe it with a diagram, okay? A diagram has encoded the whole homology of the manifold, of these persistent diagrams. So if we want to prove some kind of convergence, in terms of homology, it has no sense to say, okay, we have the convergence of a discrete set to a continuous set. But for the persistent diagrams, we can define a notion of convergence of persistent diagrams, which means convergence of the topologies. So we have the population persistent diagrams that I didn't define that, but you can define that. So you give me a manifold, you give me a distance on this manifold, and there is a way to define the persistent diagram for that manifold. And we are going to call it the diagram of M and D, the metric space. And we have what we constructed with using our Fermat distance, which is the diagram computed with a sample and with respect to this distance. And the theorem okay, then you can define a distance. I think this is easy to believe. You can define a distance between diagrams. So you can imagine, I guess that could be like homework. You can think of how to define a distance between two diagrams. So once you do that, this is called the bottleneck distance. And we can compare two diagrams, and what we can prove with Eugenio, Jimena, and Gabriel Mindlin, that the distance between the sample diagram and the population diagrams also goes to 0 as the sample size goes to infinity. Okay, so this result was very well known when you use Euclidean distance, and that's what is used. It's called the stability theorem. So it is known that that when you use Euclidean distance, you get this convergence. So the novelty here is that we replace Euclidean distance by a distance which is computed with the data. It's a distance that depends on the data, and in our case, since these distances are converging to the population distance, we can also get convergence from the convergence as metric spaces. We can get the convergence of the persistence diagrams. Okay, so the good news is that we have nice properties. One, we saw it before. The persistent diagrams computed with this distance, we got something which, since the distance does not or depends like very weakly on the ambient space, we get persistent diagrams that do not depend or depend like very weakly on the embedding that you use to embed your data in the ambient space. So you get intrinsic persistent diagrams. And in fact, as you can see, what we get is an object, which is the diagram of the manifold respect to the distance that we define, which is intrinsic. While the diagram that you get using Euclidean distance depends on the embedding that you use to embed your data. Okay, so we get intrinsic persistent diagrams. That's good news because you can put your data anywhere and you are going to get the same thing. And the other good news is that in this using this distance, the topological features persist for longer time intervals. That's what we mentioned before. Okay, and that's essentially is related to the other fact that is independent of the embedding that we use to embed our manifold in the ambient space. And there is also a third good news that I have no time to discuss it today, but thanks to the fact that that we raise our distances to the alpha, we get that our persistent diagrams are robust to outliers just for the holes, not for the connected component. But that's not the problem because it's plenty of methods to compute the number of connected components. That's very easy. And so if you want to compute the holes, then what you get replacing the Euclidean distance with the distance is a method which is much robust to outliers. So here you have an example. This is the sample of that manifold, and we compute the persistent diagram for different values of, here P is alpha. This is alpha equals 2.5, alpha equals 3, and alpha equals 3.5. As you can see that here, well, okay, you can see here you can always see the connected component. That's here. There is one hole, and here you can see there are two small holes. This is related to our question. So when alpha is not that large, you still have these two additional holes. But as you enlarge a little bit alpha, then they are not there anymore. Here you have just one hole, but you still have this problem with the connected components. You can see that here you have one hole, that's correct, but you have this problem that you have disconnected components appearing. That's because when you raise your distances to the alpha, you are more likely to have more connected components because you isolate the points. So a point which is like far away from the sample, now the distance is much larger than before. When the larger the alpha, the much larger this distance. So this has this, maybe it's not a nice effect on the connected components, that you enlarge distances and then you create spurious connected components. Okay, I think it's a good moment to stop. And we discuss applications maybe some other day. I'm going to stop here. Thank you very much for your attention.
Thanks. Thank you so much.
Last thing. So see, there you have like a lot of links in case you want to try to give a try to all these methods. You have in the first link you get you can download the implementation of this algorithm for clustering. The second link you can do your persistence diagrams. There's a tutorial about intrinsic persistent homology by Jimena in the third link, and in the fourth link we have applications to optimal transport on manifolds. Okay, now really I stop. Thank you very much. Maybe I try to put the links in the chat if I can do that.